Hello, everyone. Welcome to today's talk about distributed data processing for real-time applications, where we'll go over some latest advancements in event streaming architectures and how modern applications can benefit from it. I'm Maheedhar Gunturu, and I've been working with distributed systems as an architect for more than 15 years now, and I'm currently with Amazon Web Services as part of the worldwide specialist organization focusing on databases. So here is the agenda for this talk. I will begin with a brief overview of modern application architectures in the initial section. I will go over how application development is evolving with the help of microservices and serverless, and also outline why this is leading to event-based architectures. Then we will dive deep into the fundamentals of event processing, where I'll go over some basic terminology and also discuss advancements with the advent of newer stream processing platforms like Pulsar. We will then go over some pre-built connectors that it supports, and some of the benefits of using event processing platforms. Next, we will go over some patterns in event processing and close it out by talking about some latest advancements with data mesh architectures and so on. Modern application architectures. So if we look historically and think of mainframe, client server, three-tier, and then microservices as different phases of application development, the monolithic nature of applications is getting disrupted with microservices-based applications. A single application historically would have a single database for it would access. That is a very relatively simple architecture. With the microservices-based application, that contains many services, and each service is likely to have its own purpose-built database. Some of these services are basically part of many applications, and they have to be scaled independently along with the infrastructure like databases and message queues that support it to serve customer traffic. This changes how enterprises think about data management. And if you look at the bottom, you can see a timeline of how application integration patterns in enterprises is evolving as well. Historically, ETL systems like extract, transform, load kind of tools, which started around 40 years back, was used to combine data from multiple applications and derive insights. And it progressed with time to enterprise application integration, or EAI, and then to EII, and then to enterprise service bus, and then to complex event processing, and iPaaS in the cloud, and more recently to service meshes and data meshes architectures. What enterprises are witnessing is a rapid proliferation of data that is getting generated by modern applications like web, fintech, e-commerce, mobile, social media, IoT, and many more. Oftentimes, the infrastructure that is needed to support them needs to be scaled dynamically as enterprises cannot predict their usage. This is increasingly leading to serverless and containerized architectures that are event-driven. This may not be immediately obvious, but oftentimes a single user action, like clicking on a web page or ordering something on e-commerce or requesting for a ride via a ride-hailing app, results in a call to many, many microservices in the background. And the required infrastructure needs to be dynamically scaled based on demand. So the databases and message queues and everything needs to be dynamically scaled based on this demand. Oftentimes, this uses serverless architectures like Lambdas or event bridges or containerized systems like Fargate and so on. Usually, many applications are interested in a single event, and oftentimes each application has a separate latency budget. And this is where queuing systems can really help. Say, for example, you order something on an e-commerce site. The shipping and inventory microservice needs to update it immediately. But maybe the recommendation microservice can process this a few minutes out. And so you sort of have to make that appropriate purpose-built tools based on your use case. And the databases that are needed to support each of the microservice will vary as well. It can vary from an inventory, from an in-memory system or in-memory database that needs to respond as quickly as possible to give the best user experience, to a graph database, which helps in understanding the relationship between different entities present in a transaction. or to a key values database that simply wants to store unstructured data. So we need to pick the appropriate tool for the appropriate purpose. So use these purpose-built tools. Some of the benefits of serverless, as listed in this slide here, is you don't have to manage any servers. Typically, your service just exposes an endpoint, and that's about it. The cluster that is supporting the service automatically scales based on traffic that is hitting the service. You only pay for what you consume. So if you're not utilizing a service at any point in time, then you don't have to pay for it. It is almost like a utility model. Serverless enables event-driven architectures, where a single user action can result in infrastructure getting provisioned in multiple microservices. And this is very important, especially for event messaging and streaming platforms. So the capacity needed for it can be dynamically provisioned for it. All of this is triggered using services like Lambda, your event bridges, and different event-driven architectures, where developers just have to write the business logic for their code. And things related to the infrastructure, like versions of Java or Python, or standing up an application server, or container orchestration, all of this is taken care of by the platform. So here is a quote that I really like from Tim Bray, who's a thought leader in event-driven architectures. If your application is cloud native, large scale, or distributed, and doesn't include a messaging component, that's probably a bug. This quote really speaks to the significance of event processing platforms. So let's dive into some of the fundamentals of event processing. So what is an event? An event is a change in state or an update that carries entropy and has a timestamp associated with it. Events can carry, either carry state or simply be identifiers, like notifications of that like. Event-based architectures have three key components: event producers, event routers, event consumers. Now that we understood what an event is, let's define an event stream. A series of continuous events that represent the changing behavior of a system form an event stream. Streaming, though it might appear very simple at first, combining events from many streams and or enriching it with other data sources in real time can deliver useful, actionable insights. This is also called stream processing. So here is a pictorial representation of what we discussed in the previous slide. On the left, you have a variety of data sources like IoT devices, point-in-time transactions, microservices emitting events, or change data capture logs from databases. These are producing data. This data is then stored and organized in topics that are made available to various sinks or consumers that are on the other side of the slide. A variety of applications or databases consume this data, or even create operational alerts based on this data. So let's try to understand some basic terminology of message queues, or pub/sub-based systems, or like they were called before a while back. So you have a publisher, or sometimes called as a producer, that is generating the data. Then you have brokers, which is a distributed layer, where the produced data gets stored. The data in the broker is organized by topics and is stored in a queue. Each topic is then subdivided into partitions, and then each partition has a primary and a replica. The topic contains messages or events, and each of them has an offset ID associated with it. Then you have a consumer or a subscriber consuming the data from the broker. In the simplest form, you don't really need like a schema for the event or a message, but most systems have really evolved to include a schema registry, which helps with consuming the event while deserializing. There are a few event-based platforms like Kafka which have championed this architecture. But let's explore how Pulsar advances this even forward. Apache Pulsar is a real-time messaging and streaming platform built for cloud-native architectures. Apache Pulsar has a few additional benefits when compared to Kafka. I'm going to briefly touch upon those differences. It has its own storage engine with Apache Bookkeeper. Topics are broken into partitions and then further broken into segments, which store the data in Bookie nodes. This effectively separates storage and compute, which is a very important thing. Brokers can store a lot less data now, and they can scale seamlessly. So to handle like additional or spiky traffic, this makes the broker stateless and can easily scale. Because of these changes, there are some additional terminology that you would need to understand. Like topics in Pulsar are stored as segments. Each topic segment is replicated, which allows for concurrent reads and high throughput. A cursor, which is very similar to an offset, is the subscriber position for a consumer. A consumer is a process that establishes a subscription to a Pulsar topic and processes messages published to that topic by the producers. Namespace is a grouping mechanism for related topics. And namespace bundles is a virtual group of topics that belong to the same namespace. A subscription is a lease on a topic, so basically established by a group of consumers. And Pulsar has 4 different subscription modes like exclusive, shared, failover, and key shared. Tim is going to cover more details related to this in his talk later. Pulsar readers are more like consumers, it's sort of very interesting like how the differences are here. Pulsar readers are more like consumers, but with 2 crucial differences. While consumers always begin processing with the latest available message, with readers you can specify the cursor or offset from where messages can be processed. Also, readers don't acknowledge messages. ACK in Pulsar is Pulsar's way of knowing that the message has been processed and can be deleted from the system. If no acknowledgement is sent, then the message will be retained until it's processed. There's also something called NAC, which is a negative ACK, to signal the consumer, Pulsar that the consumer has failed to process a message and it should be replayed at a later point in time. Bookie is a single node of Apache Bookkeeper. We already spoke about segments, but basically a topic is broken into segments and is replicated and stored in Bookie nodes. Dispatcher is an asynchronous TCP server that uses custom protocol to transfer data in and out of brokers. Ledger is an append-only data structure in Bookkeeper that is used to persistently store messages in Pulsar topics. Tenant is an administrative unit for allocating capacity and enforcing an authentication and authorization mechanism. So that sort of covers most of the basic terminology that you should be familiar once you want to deal with these advanced systems. But that's just a start. So another significant benefit of using Pulsar is you get multi-tenancy out of the box. This helps applications that need to work in a shared environment where there's clear separation of responsibilities. So each Pulsar instance can have multiple Pulsar clusters, and then each cluster can have multiple tenants inside of it. And this allows for different departments or teams within an organization to share Pulsar clusters, which is a really neat feature and a powerful feature that's just available out of the box. Each tenant can have many namespaces as part of it, and each of the namespace allows teams to keep their data separate from the rest of the organization. Each namespace contains many topics and can have its own policies, and they group further into namespace bundles, which is how the consumers consume based on various subscription modes. Both Kafka and Pulsar support global replication, but how it's done is a bit different. Both systems replicate the data asynchronously, but Kafka, you would need to use something like Mirror Maker, which replicates the data. Oftentimes, a little unwieldy tool, but you might have to use that tool for doing global replication with Kafka. But with Pulsar, geo-replication is available out of the box. Really sort of catch those, like you have to use a global zookeeper cluster, which is used to store the tenants and namespaces and policies, and it allows individual Pulsar clusters also to remain in sync. This data doesn't really change that frequently, though. There are clients available in a variety of languages like Java, Go, Python, C++, Node.js, and a few community drivers with Rust and so on. And so the community is evolving, and definitely there is interest. You can query the data stored in Pulsar via Presto SQL, and it is integrated with Schema Registry as well. Pulsar also supports most Kafka clients with the help of its client wrapper. And that's a very neat functionality to have. Flink provides an Apache Pulsar connector for reading and writing data from and to Pulsar topics with exactly once guarantees, which might be very useful in some cases. There's also a Spark streaming adapter, which can receive raw data from Apache Pulsar. Pulsar also supports connecting to multiple protocols like Kafka and Pulsar, and MQTT, and AWS SQS connector, AWS Lambda connector. It has a Scala DB connector, and many more. Pulsar also supports function meshes, which is an operator that enables to run Pulsar functions and connectors natively on Kubernetes. It's a pretty neat functionality to have. And sort of systems are evolving in that direction. It provides a variety of messaging delivery guarantees when consumers are operated in various subscription modes, as we have spoken before. It is integrated with the Schema Registry and also has built-in instrumentation with a lot of detailed metrics for observability. So now let's go through like some of the benefits of using event processing systems. It's almost like a summary of all the benefits till now. They provide event streaming platforms, provide a centralized platform for managing event-driven communication between various applications. They provide an intermediate layer for buffering communications between applications. Different applications process data at different speeds, and you can use message queues to manage impedance mismatch between them. Data can be exported and imported via various connectors, pre-built connectors, which are oftentimes available out of the box. Databases and applications can publish changes via change data capture for downstream app systems to process this. And it's very important to use these change data capture. It's a very optimized way of sharing data between the different systems. If a stateless application were to lose its state, it can recreate the state based on the data that is stored in other databases using these connectors. Streaming platforms provide the ability to do streaming data transformations that is consumed by downstream applications. Any applications basically can now seamlessly integrate with the data from other applications using these pre-built connectors. With the help of function meshes, you can create workflows that provision the necessary infrastructure underneath to process the data in real time. So these are like sort of some of the benefits which most enterprises are getting using event streaming platforms. In this section, I'll go through some patterns in event processing. Basically, event processing can be broadly classified into these three different architectures. These are like in event-driven architectures, event streaming architectures, and event sourcing architectures. So if we sort of double click on what each one of them is, you would see like in event-driven architectures, you can use message queues to route messages and decouple microservices and build sort of independent units of cohesion for them. And this also enables async and synchronous communication, and also establishes sort of decoupling for microservices. In event streaming architectures, you would do real-time transformations of data, where you can do things like aggregates and filters and sliding window type computations on this data. And this really helps in transforming the data in pretty close to real time, and provides all this really nifty functionality, almost like real-time ETL. In event sourcing architectures, you're typically looking to store the data long-term, maybe leverage pre-built connectors for this. But some of the patterns here are CQRS, or command query responsibility separation. This is an important design pattern. It is a pattern that treats data separately it's a pattern that treats retrieving data separately from changing or updating data. And it provides things like event stores or message queues in the middle, where the data is stored oftentimes for fairly brief periods of time. And it sort of separates out the reading part of it from the writing part of it. Next is stateful service pattern. This is a way where within the bounded context of a microservice, or a group of microservices, state can be shared and can be updated by different microservices, oftentimes even concurrently. Then there is the Saga pattern. The Saga pattern is a failure management pattern that helps establish consistency in distributed applications and coordinates transactions between multiple microservices to maintain data consistency. So if a transaction were to fail in a downstream system, then it would reverse the entire event loop for it. Okay, so we're in our final topic, where we're basically going to go over data mesh architectures. Data mesh is a set of core principles that describes how to design modern data architectures where data from various parts of the enterprise is shared in a secure way to overall make the enterprise data driven. And all of this is done in a very technology agnostic way. So it's more like it's a set of principles which make this possible. Basically, this provides a framework where data from microservices, databases, event streaming platforms, and data warehouses to be shared in a secure fashion. This data is then leveraged by cross-functional teams to make better decisions. So the basic principles are: data is a product. So data is no longer a cost center only. It also becomes a source of revenue. Each organization owns their data end-to-end. They're responsible for building, operating, and serving their data. They need to publish change data capture logs across bounded context to downstream systems so that downstream systems can leverage it. And teams need to resolve any issues and when it comes to sharing with the data and the infrastructure needed for it, and make it easy to discover data. The next important point is around federated data governance. So features like data lineage, validating data qualities, and securely sharing data with the appropriate access controls are enforced. And things like auditing and reporting should be enabled as well. And finally, the platforms that enable this need to be self-service with purpose-built tooling. That means it should be accessible to business analysts and data scientists or developers to easily access this data and sort of build business processes on this data. Well, that's it for today. Thanks for this session. Thanks for attending this session. Feel free to stay in touch with me.